press the bell icon on the YouTube app and never miss another update.
Hello students, in the previous class we were discussing about current density. Current density at any point in a current carrying conductor is the current distributed per unit area of cross section around that point. This current density is a vector quantity, right? The direction of current density is same as the direction of flow of positive charges in the conductor, right? In other words, right, the direction of flow of positive charge in an electric field is in the direction of electric field. Therefore, the direction of current density is same as the direction of applied electric field at that point in a conductor. Now, let us derive the relation between current density and applied electric field. Now, expression for current density, that is to show that vector J is equal to sigma into vector E, where sigma is a constant for given material of a conductor at constant temperature called conductivity of the material of the conductor, right? Now, to derive this relation, now let us consider a conductor a cylindrical conductor of length L and area of cross section A. Let a potential difference be applied across the ends of the conductor. Now this potential difference, right, establishes an electric field inside the conductor from higher potential to lower potential. Now under the influence of this external electric field, the free electrons, right, acquire a very small drift velocity Vd in the opposite direction of applied electric field, constituting an electric current. Let I be current flowing through the conductor. Right. So far in the previous classes, we have derived expressions for drift velocity of free electron and current flowing through a conductor using those two expressions. Now, drift velocity of free electron, right, V d, here we are considering only the magnitude. So E tau by m, where E is charge of electron, now m mass of electron and tau relaxation time. Now again, so current in the conductor. Current in the conductor I is equal to NEAVD. Let us take this as equation 1 and this as equation 2, where N is a free electron density, A is area of cross section of the conductor, Vd is drift velocity. Here N is a free electron density of material. Right. Now, substituting equation 1 in equation 2, we get I is equal to, right. Now, this is NEA, substituting for drift velocity. Now, this is E tau by M, or I is equal to right, N E into E square tau E by M. So, I have rearranged this equation. Let us take it as equation number 3. In the next derivation, the steps are almost same while deriving Ohm's law. So, we got equation 3, I is equal to N E square tau, right, A E by M. Now, this equation 3 can be written as I by A is equal to N E square tau by M into E. Let us take it as equation number 4. Now, the terms I have written inside the bracket are constant terms generally, right. Now, by definition of current density, we have current density at any point, right, in the conductor. J is equal to I by A, where I is current in the conductor, A is area of cross section of the conductor. Let us take it as equation number 5. Now, comparing equations 4 and 5. Comparing equations 4 and 5. So, we get J is equal to right, N E square tau by M into E, right. Here E is electric field, J is current density, or I can write J is equal to sigma into E. Let us take it as equation number 6, right. Here sigma is equal to N E square tau by M is a constant, right, called electrical conductivity of the material of the conductor. It is constant for a given material at constant temperature, right? Its value changes with temperature and its value is different for different materials, right? Now copper has different value of conductivity, right? Silver, right? Aluminum, etc. Now here where sigma is equal to this n e square tau by m. Let us take it as equation number 7, right? Where sigma is constant for given material at constant temperature called electrical conductivity. So called electrical conductivity, right? Now this equation 6, right, in vector form, equation 6 in vector form can be written as vector j is equal to sigma into vector e. This is the required equation, that is expression for, right, drift velocity of current density in terms of electric field, where sigma is a scalar quantity, and this equation is called right, Ohm's law in vector form, right? This equation we will take it as 7, right? Sorry, equation 8. This equation 8 is Ohm's law in vector form, or this is an equivalent form of Ohm's law, right? So this derivation is generally asked in board examination for 5 marks. So sometimes, so the question will be like that, right? Derive the relation sigma is equal to n e square tau by m, where the symbols have usual notation. In that case, the questions will be direct. You have to derive this equation sigma is equal to n e square tau by m, where we need not have to arrive at this point, right? So anyway, after this one, just taking equation 6 in vector form. Right. Now, let us take another derivation, that is deduction of Ohm's law. Again, it is a 5-mark question in board examination. We all know that, even we have discussed in right 10th standard, Ohm's law, right? That Ohm's law gives the relation between current flowing through a conductor and potential difference applied between the ends of the conductor. It gives relation between current I and potential difference V, right? Now, we are familiar with the statement also. It states that at constant temperature and other physical conditions remain the same, electric current flowing through a conductor is directly proportional to potential difference between ends of the conductor. That means current I is directly proportional to potential difference V, right? Now theoretically, right, or mathematically we can prove that relation. I is directly proportional to V. Now the starting point is same, right? It is very much similar to what we have derived the previous derivation, that is J is equal to sigma into E, but where we have taken current density and electric field, here we are taking current and potential difference, right? All otherwise almost the derivation is same. Now again let us consider a conductor of length L and area of cross section A. Let a potential difference is applied across the ends of the conductor. Let V be potential difference between the ends of the conductor. As usual, that applied potential difference, right, now establishes a uniform electric field inside the conductor directed from higher potential to lower potential. Under the influence of this electric field, right, free electron, right, acquire a drift velocity Vd in the opposite direction of, right, electric field, constituting an electric current. Let I be the electric current flowing through the conductor, right, and V be the potential difference. Again we have drift velocity. Drift velocity Vd is equal to E tau pi m. Let us take it as equation number 1, where E is charge of electron, right, m mass of electron, and tau is relaxation time. Again, from the expression for current in the conductor, now we have current in conductor. Current in conductor. Now that I is equal to N E A V suffix D. N is free electron density of the material of the conductor, E is charge of electron, A is area of cross section of the conductor, and Vd is drift velocity, where N is free electron density of material of conductor. Now taking this as equation 2, now again substituting equation 1 in equation 2, right, we get, right, I is equal to N E A into E tau by M, or this is equation 3, or we can write this equation as I is equal to n e into e square tau by m, right, tau by m into a into e, right, where E is electric field, A is area of cross section of the conductor. Let us take it as equation number 4. Up to this one, the derivation is same. In previous derivation, we have taken, right, I by A and I by A is equal to J, right? But now we are deriving the relation between current and potential difference. Right. Now we have, right, electric field applied to the conductor. From the relation between electric field and electric potential, we have E is equal to V by L. Let us take it as equation number 5, where V is potential difference between the ends of the conductor and L is the length of the conductor. Now, substituting equation 5 in equation 4, we get I is equal to n e square tau by m. These terms are taken inside a bracket. Now we left with A, right? That I will take that A here. Now that E is equal to V by L. So I will take A by L inside the bracket into V. Because for a given conductor, area is constant and L is constant. A and L may be different for different conductors, right? But for a given conductor, A and L are constant, right? Now let us take it as this equation. Now equating it to V, right? So this V is equal to, right, now this term m by n e square, m by n e square tau. Now cross multiplying this one, we have this L by A into I. So equating this equation by taking the entire term, right, n e square tau by m into A by L towards left side, right? So we got this equation. Now let us take it as equation number 6. Right. Now we have this equation here. This V is equal to sigma L by A into I, where sigma is equal to, sorry, we'll take this, not sigma, this is rho, where rho is equal to m by n e square tau. Let us take it as equation number 7, where rho is constant for given material called electrical resistivity. It's called electrical resistivity of the material of the conductor. In fact, this n e square tau by m is conductivity. Its reciprocal is called resistivity, and rho is equal to m by n e square into tau. We have taken it as equation 7. Now, from this equation, we can write I is equal to, write R, V is equal to R into I, equation 8, where R is equal to rho into L by A, equation 9. Right? So far we have derived that. V is equal to rho into, right, L by A into, right, V. So replacing that rho, L by A by R, where R is constant for given conductor at given temperature called electrical resistance of the conductor. See here, rho is constant for given material, of course at constant temperature, called electrical resistivity. But resistance is constant only for given conductor. It is not for material. It is given for conductor. But resistivity is constant for material of the conductor. Right. Now, from this equation, so since R is constant, we can write V by I is equal to constant, or I is directly proportional to V. So from this equation, V is equal to IR. Since R is constant, V is directly proportional to I, or I is directly proportional to V. Now hence, right, we have arrived at Ohm's law. Here we have derived, right, I is directly proportional to V, but we got two more expressions here. One for electrical conductivity and another is for electrical resistance. Now generally there will be 5 more questions on in board examination, right? Directly there is the question will be deduct Ohm's law. Right. Now so far we have derived two expressions. In these two expressions, deriving these two expressions, so we have some important relations. So number one, we have electrical conductivity, right? Sigma is equal to n e square tau by m. Let's take it as equation 1, where n is free electron density, E is charge of electron, tau is relaxation time, and m is mass of electron. Number 2, we have electrical resistivity. It is also called as specific resistance, right? Rho is equal to m by n e square tau. Let us take it as equation 2. Now from equations 1 and 2, we have rho is equal to 1 by sigma, or sigma is equal to 1 by rho, right? Resistivity is defined as the reciprocal of conductivity, or conductivity is defined as the reciprocal of resistivity, right? Here, smaller the resistivity, higher is the conductivity. Higher the resistivity, smaller is the conductivity. Here, both sigma and rho are constants for given material at constant temperature. It is because here n is constant for the material, E and m are general constants. Only in these two equations we are having tau, that relaxation time. In fact, relaxation time depends upon the temperature. Relaxation time is inversely proportional to temperature. As the temperature increases, the relaxation time decreases. Therefore, these two are constant at constant temperature. If temperature changes for the same material, there will be change in both conductivity and resistivity. And of course, it has different values of values for different materials, right? So among the materials, silver has the lowest resistivity and the highest conductivity, right? It is followed by copper and aluminum. We will discuss it later, where we will go to discuss this resistivity in detail. Right? Now the third one, we have electrical resistance. R is equal to rho into L by E. Take equation 3, right? Where rho is resistivity, L is length, and A is area of cross section. Or R is equal to, we have rho, this is m L by n E square tau into E, right? This is another expression for electrical resistance. R is equal to m into L by n E square tau into E, right? Now this R is constant for a given conductor at given temperature. Suppose if I have two copper pieces, say this is one copper piece, this is another copper piece, right? Now resistivity and conductivity are same for these two, right? Because material is same, but electrical resistance is different. You see, length of this one is more than length of this one, this chalk piece, right? Say copper piece, right? Now, as resistance is directly proportional to L from this equation, obviously it has more resistance and it has less resistance, right? So, if I take this one, it is a given conductor, then the resistance remains constant at constant temperature. And fourth one, we have current density J is equal to sigma into E in vector form, right? Let us take it as equation number 4, or we can write vector J is equal to, right, E by rho, where rho is the reciprocal of electrical conductivity. So, in terms of resistivity, the current density is given by J is equal to E by rho, and this is Ohm's law in vector form. And fifth one, we have Ohm's law, that V is equal to I into R or R into I. Is that clear? Now, we shall take up Ohm's law, one of the important laws in current electricity, Ohm's law. Now, we are familiar with the statement, right? It states that at constant temperature and other physical conditions remain same, electric current flowing through a conductor is directly proportional to potential difference between ends of the conductor, right? The statement. Now, at constant temperature and other physical conditions remain same, electric current flowing through a conductor is directly proportional to potential difference between ends of the conductor. Ends of the conductor, right? Now, let us explain this law. Now, here we have taken other physical conditions remains the same, right? Now, the conductor is not subjected to any stress, right? That means it is not under pressure, mechanical pressure, or magnetic field is not applied to the conductor, right? So these are all certain other conditions. So there is no stress on the conductor. There should be no, right, applied magnetic field on the conductor, right? Now, let us consider a conductor, right, represented by the symbol like this, sawtooth, right? And it is called resistance or a resistor, right? Now, this is R is the symbol used for resistance of a conductor. We have considered a conductor AB, right? Now, a potential difference is applied across the ends of the conductor, and a current I flowing through the conductor, right? Now, see here, the conditions for the flow of electric current between 2 points. Now, condition number 1, there must be a potential difference between the 2 points. Condition number 2, there must be a conducting path, right? That conducting path is provided by a conductor. Now, it is represented by R, right? Now, according to Ohm's law, at constant temperature, and of course other physical condition remain same, so current is directly proportional to, right, potential difference. That is, I is directly proportional to V, or V by I is equal to constant. This is the mathematical form of Ohm's law, right? According to Ohm's law, at constant temperature, current is directly proportional to potential difference, or according to Ohm's law, at constant temperature, the ratio of potential difference across the ends of the conductor to current flowing through it is constant, that V by I is equal to constant, right? Now, this constant, right, is denoted by R and is called, right, electrical resistance of the conductor, or this V by I is equal to R, that is electrical resistance or simply resistance of conductor, right? Or from this equation we can write V is equal to IR, right? This equation gives the relation between potential difference, current and resistance. Strictly speaking, this V by I is equal to constant is the true Ohm's law. From Ohm's law, we have obtained this equation, V is equal to IR, right? But this V is equal to IR gives the relation between, right, potential difference, current and resistance of any component, right? You got my point? It is any component. It may be conductor or it may be, right, semiconductor, right? So this V is equal to IR. Now, we have taken the statement of Ohm's law and we have given explanation of Ohm's law. So note points. Now from Ohm's law we have V is equal to IR. From this equation, write A. Current in the conductor. So current in the conductor I is equal to V by R. If we know potential difference between the ends of the conductor and resistance R of the conductor, then we can calculate the current flowing through the conductor, right? That means with the help of Ohm's law, we can find what is the amount of current flowing through a conductor of resistance R when potential difference applied is V. B. Now we have resistance of conductor. R is equal to V by I. If we know potential difference and current, then we can calculate the resistance of the conductor. Now see, when right R is constant, right, I is directly proportional to V. That means when R remains constant, we can increase the current in the conductor by increasing the potential difference. When V is constant, right, in most of the cases V remains constant because any source of EMF, a cell or a battery that provides a constant potential difference, right? In that case, I is inversely proportional to R. Current flowing through a conductor is inversely proportional to the resistance of the conductor, right? Now this equation is very important. When we have constant potential difference provided by a cell or a battery, then current can be controlled by using resistance. When we increase the resistance, current decreases. When we decrease the resistance, current increases. So a resistance can control or regulate current in electrical circuits. Right. Now another important point here. Now we have V is equal to IR. Here what is V? Potential difference is equal to current into resistance, right? So potential difference across a conductor is equal to the product of current and resistance in the conductor, right? Therefore potential difference is also called IR product. This potential difference is also called as a IR product. Actually this term IR product we are going to use in Kirchhoff's laws of electrical network. And the third one, we have potential difference. V is equal to IR. We take equation 1. And also we have potential difference. V is equal to W by Q. Right? Remember the definition of potential difference, right, in electrostatics. Potential difference between any 2 points in an electric field is the amount of work done in bringing a unit positive charge from one end of the conductor to the one point, a point of lower potential to point of higher potential, right? So here, when Q is equal to plus 1C, then, right, V is equal to W, that is equal to IR. Now, the significance of this potential difference or IR, right, is that it represents the amount of work done, right, in transferring 1 coulomb of charge from one end of the conductor to the other end of the conductor against the resistance of the conductor, right? That means, right, potential difference V or IR product is the amount of work done in driving unit positive charge from one end to other end of conductor against the resistance of the conductor. Against the resistance of the conductor, right? In fact, this resistance R is the opposition offered by a conductor for the flow of current through it, right? To overcome that opposition, right, we have to spend energy or to do work, right? Therefore, potential difference between the ends of the conductor, which is equal to IR product, is the amount of work done in driving unit positive charge from one end of the conductor to the other end of the conductor against resistance of the conductor, or potential difference is the amount of work done to maintain a steady current in the conductor against the resistance of the conductor. It is just like while driving a vehicle on a level road, smooth level road, we need to on the engine. If we switch off the engine after traveling through certain distance, the vehicle comes to rest. Why? It is because of the friction, right? So when we are moving with a constant speed on a level road, why we need an engine, right? So that engine does work against friction so that it can maintain a constant speed. In a similar way, potential difference is the amount of work done to maintain a steady current in the conductor against the opposition or resistance offered by the conductor. Remember this point, potential difference is equal to work done is equal to IR product. Why I am stressing this thing is, right, again we need to derive an expression for current in a circuit in terms of EMF, external resistance and internal resistance, where we are using this concept. Work done is equal to potential difference, which is equal to I into R. Now we will take another concept. resistance R. Now, electrical resistance or simply resistance of a conductor is the opposition or obstruction offered by the conductor for the flow of electric current or electric charges through it, right? So, the qualitative definition or meaning of resistance, right? Now, resistance of a conductor is the opposition or obstruction offered by the conductor for the flow of electric current through it. Now, what is the cause for resistance of a conductor, or what is the origin of resistance, right? A conductor offers opposition or resistance because of the collision of free electrons, right, moving with drift velocity with the heavy positive vibrating ions of the conductor, right? Now, right, resistance of conductor is due to collision of free electrons, right, moving under electric field. That means average velocity is drift velocity, right? The resistance of conductor is due to collision of free electrons moving under electric field, right, with heavy vibrating positive ions, right? This collision offers opposition or obstruction for the flow of current in the conductor. Suppose if we consider a conductor, right, so when we applied an electric field, say E, a free electron, say starting from this point, it gets accelerated and collides with this ion, an ion, right, and its velocity decreases. Now here, the path of electron between two collisions is not a straight line. It is somewhat a non-linear curve because it is subjected to two velocities. One is velocity acquired under the influence of electric force due to electric field, and another one is a thermal velocity, right? Now here it changes its direction and move to another ion. Again here it collides, then changing the direction, here it comes to collide with another ion, right? Again here it moves like that, here again collides, and here it reaches this point, electron, right? So, due to this collision, the velocity of the electron decreases. Remember, I is equal to NEA VD, I is directly proportional to drift velocity. Due to collision, there is a decrease in the value of drift velocity. As drift velocity decreases, automatically current decreases. Current decreases means it is opposed by the conductor due to collision. Moreover, the path of free electron from one end of the conductor to the other end of the conductor is not a straight line path, right? It is in fact a zigzag path, right? Just like moving a vehicle on a continuous hump, right? Automatically when we are moving on a continuous hump, speed of the vehicle decreases, right? Here also the speed of electron decreases, and that is due to the collision of free electrons with the vibrating ion. So what is the origin or cause for resistance? It is the collision of free electrons moving under the influence of electric field with heavy vibrating positive ions. Now, how to measure resistance of a conductor? Now this is resistance is the opposition offered by a conductor for the flow of electric current is a qualitative statement. It gives what exactly the meaning of electrical resistance. Then how to measure that electrical resistance? We can measure electrical resistance of a conductor by using Ohm's law, right? That gives a quantitative definition for electrical resistance, right? Now, definition of electrical resistance, right? Now, from Ohm's law, we have V is equal to IR, or R is equal to V by I, right? Where what is R? R is resistance of conductor. What is V? It is potential difference, right, between the ends of the conductor. And what is I? It is current flowing through the conductor. Therefore, electrical resistance of a conductor is defined as the ratio of potential difference across the ends of the conductor to the current flowing through it. By measuring potential difference across the ends of the conductor using a voltmeter, by measuring current through the conductor using an ammeter, we can measure resistance of the conductor using R is equal to V by I. Now, if we take SI unit of resistance, SI unit of resistance is Ohm. It is denoted by the symbol capital omega, right? Now again, by definition we have R is equal to V by I. Now Ohm is equal to, that is the unit of electrical resistance, Ohm is equal to unit of potential difference, that is volt, unit of current, that is ampere. So Ohm is a equivalent unit of volt per ampere. So actually unit is volt per ampere and it is named as Ohm. So when V is equal to 1 volt and I is equal to 1 ampere, from this equation R is equal to 1 volt per 1 volt per ampere, 1 volt per ampere, right? That is equal to 1 ohm. So when 1 volt of potential difference applied to a conductor causes a current of 1 ampere in it, then resistance of the conductor is equal to 1 ohm. Therefore, ohm is defined as a resistance of the conductor that produces 1 ampere of current when a potential difference of 1 volt is applied to it, right? Or resistance of a conductor is said to be 1 ohm if a potential difference of 1 volt applied across the ends of the conductor produces a current of 1 ampere, right? So we have discussed what is the meaning of electrical resistance, what is the cause or origin of electrical resistance, quantitative definition of resistance, and SI unit of resistance, that is ohm, right? And ohm is defined in such a way that, right, the resistance of a conductor is said to be 1 ohm if a potential difference of 1 volt across the ends of the conductor causes a current of 1 ampere.